Yeah, I'll show you how to do it. It's good.
Yeah, I want.
Button. Okay, so hello everyone. Welcome to the fourth session of the MathStat Virtual Tea. And so today it's my great pleasure to introduce our speaker, Narayanan Rangaswamy. Narayanan got his PhD in the Department of Electrical and Computer Engineering at Duke University in May 2020, under the supervision of Henry Pfister and Robert Cotterbank. He is now a postdoc researcher at the University of Arizona in Tucson, working with Bang Visk. As a graduate student, Narayanan is truly a rising star in the field of quantum error correction. He addressed a long-standing question in fault-tolerant quantum computation via a perspective rooted in classical coding theory. So today, he's going to introduce us to what is quantum computing and how does quantum error correction work? So please join me and welcome our speaker today.
Thank you, Shanshan. So let me start sharing my screen. Okay, can you see my screen?
Yes.
Okay. And can you also see my cursor?
Yes.
Okay. Thanks again for the nice introduction, Shanshan. Thanks for inviting me to give this talk. I'm very excited. Yeah, so I recently graduated from Duke, and then I was a research associate at Duke for the summer. And just this week, I started working with Professor Bane Vasic at the University of Arizona. So this is officially my first postdoc talk. All right, so I'm going to, so the structure of my talk is going to be a little bit of history, and then just to give you a glimpse of, the big higher level things, where the field is today and like what sort of problems we are thinking about, and like the different sort of research areas within the global quantum umbrella. And yeah, after a little bit of that, I'll start with the basics of quantum computing, like what are the basic things, operations, etc. And then in the last section, I'll talk about, I'll start with classical error correction or coding theory. I'll introduce the basic idea, and then we'll sort of translate that to the quantum world. And then I'll finish with some of the work. I'll briefly just mention some of the work we have done during my PhD in this context. And that's how this will go. So let me start with a little bit of what the state of the art is. So I mean, quantum mechanics, of course, started at the beginning of the 20th century. So the physics community has been actively sort of refining the theory, and now it has stood up to a lot of tests. So we have a concrete theory that is also mathematically precise. But quantum sort of information or quantum computing is essentially like 3 decades old. So in the 80s, Professor Richard Feynman suggested that like these, I mean, if you want to simulate a quantum system, if you have to sort of understand how it works, then with the number of particles that are increasing in the system, the actual computational space grows exponentially. And so it's very hard to simulate it on a classical computer. So, and so he suggested that maybe it's a good idea to build a quantum mechanical computer that could simulate other quantum systems, because it's naturally working with these quantum phenomena. So that was, the first idea of like, actually trying to build a quantum computer. And then people worked a little bit on algorithms and like, tried to make a case for why this is useful to do. And after some like initial progress in 1994, Professor Peter Shor, now at MIT, so he has this now famously called Shor's algorithm, which is an efficient quantum algorithm to factor large integers. And so it gives you an exponential scaling compared to what the best known algorithm on classical computers. And that has repercussions in many fields, and primarily sort of security, because all the public key crypto systems are based on, factoring large integers, like the hardness of factoring large integers. That's where the security lies. And so people suddenly woke up, and then in the mid-90s is when this sort of quantum revolution happened. I'm of course ignoring a lot of details, but just to give you a glimpse. So yeah, so 90s is where this field really got kickstarted. And I think in the last two and a half decades, we've made a lot of progress, both theoretically and experimentally. So these are kind of examples of, systems that are available today. So now it's no more just theory. It's actually, people are actually building these things. So D-Wave is a Canadian company, which is probably the first quantum computing company that started a while ago. They have these machines that are based on something called quantum annealing. So, so these are sort of, they have like thousands of qubits, but the thing to keep in mind is that they have been shown to be useful for specific problems. So they might not be universal quantum computers, but certainly for some kind of optimization problems, a lot of people have shown that you can map it to the hardware on the system and solve them efficiently. But whether it's truly universal, I think is an ongoing debate. So that's D-Wave on the top left. And then clockwise next, you have IBM, which you might have heard a lot in the news. So IBM has these quantum computers, and they're also doing a great job in actually teaching quantum to a lot of people. Though they hold summer schools and they have a lot of resources, you can actually try running things on their computer online, etc. So this IBM system is based on something called superconducting qubits. So there are different technologies to build a quantum computer, and IBM and Google below the bottom right picture. So those two are using sort of superconducting qubits to build these systems. And lastly, in the bottom left, you have IonQ, which is a startup started by Professor Christopher Monroe from originally at University of Maryland, but he recently moved to Duke, or he will move to Duke, I think. And Professor Jung-San Kim, who's at Duke. So it's their startup. It's in Maryland. So they are using, they are trapping ions in vacuum and then using lasers to manipulate the energy levels of these ions, and that's how they are building a quantum computer. So these are the two leading technologies: ion traps and superconducting qubits. So that's the kind of systems we have, to give you some perspective. Now, the recent exciting result, which made a lot of news, is this quantum supremacy experiment that Google claimed. So roughly speaking, sort of ignoring the details, what they showed is that for a specific kind of quantum problem, they were able to use their quantum computer to sort of produce statistics that is impossible to produce in the same amount of time on a classical computer. Meaning they basically showed that it's not a classical computer hiding in there. So no classical computer could have actually cheated to produce the same results. And so they show that for this problem, which is based on sampling random circuits and then producing the output statistics, they showed that their processor, which is called a Sycamore processor, and it has 53 qubits, which means the computational space is like of size 2 to the 53, of dimension 2 to the 53. Yeah, just think of a vector space of that dimension. And so they showed that what their processor can do in 200 seconds, by their estimate, would take like about 10,000 years for the best supercomputer on Earth to do. Now, the exact sort of numbers is being debated. So for example, IBM had a challenge. They did not actually sort of prove by doing an actual experiment on their Summit supercomputer, which is the largest supercomputer we have today. But they showed that they showed some calculations that suggest that you can actually do it in a few days. So there's some numbers game being played, but even if it's a few days, this is like 3 minutes versus a few days, which is still pretty big. But I think it's a very impressive experiment because it's very hard to get these sort of fragile qubits to work properly and then actually have control on them. So I think the Google hardware team did a great job in pulling off this experiment. Okay, so yeah, so now based on that big picture, if we sort of go up and ask ourselves, so where can we apply these things? Where can we apply quantum technologies? And then these systems currently are very noisy, like the underlying qubits, which quantum bits, as we call qubits, they are very noisy, and all the operations you do, all the hardware is super noisy. And so how do you make this thing reliable? So how do you make a reliable system out of these unreliable components? And if you manage to build one, how can you use it? So those are, natural questions to ask. So of course, one area is computing itself, where you want to do things that are beyond the capability of supercomputers. And we saw a glimpse of that in the Google experiment. And here I'm sort of splitting algorithms and computation. They are so very related, of course, but by computation, what I mean is if you want to build these circuits, you actually need a good mathematical theory of these circuits. So what are your fundamental operations and how do you build more complicated operations based on these fundamental ones? So that's a mathematical theory. And then once you have this theory, you also have to worry about how do you realize this in hardware. So when I say computation here, I'm sort of putting theory plus experiment into the same umbrella. Whereas algorithms is sort of purely computer science. So like quantum computer science, if you like, where you analyze algorithms, you produce algorithms to solve problems, and then you analyze their complexity and so on. Okay, so those are two things. And of course, to tackle noise, we need a tool. And the key tool which everyone agrees on is called error correction. And we'll see this in the later part of the talk today. You can correct errors actively by sort of, finding what happened, like poking at the system, finding what happened and then fixing them. Or you can also design some passive methods where you sort of design your computation in such a way that it is resilient to some kind of noise, meaning the noise doesn't even affect it for you to worry about active correction. So there are different ways to fight noise. Yeah, I mean, you can think of all of these as like different research areas in quantum. And some are also applications, but error correction, I guess, is not an application. It's something you need to build the system. And then there's information theory, which worries about how do you store information in quantum systems? How do you retrieve them? And how does the stored information behave, etc. So this is rooted in also classical information theory, which was started by Claude Shannon in like 1948, where people worry about how do you store and process information. That was for bits, like classical information. Now we also have a theory for quantum information. That's another area to work on. And information theory sort of spans all of the other things as well. And then there's communication. So if you have like an optical channel, it's so like deep space optical communications. It's actually a quantum channel, but today the way we process information passed through these channels is sort of suboptimal because we are not using the quantumness of the channel. So people worry about how to optimally communicate over quantum channels and how to build communication systems based on that. That's another area. And then there's metrology. So quantum metrology is the idea of making very precise measurements of physical quantities. So you might have heard, like last year, the SI units, the international standard for units was updated last year, meaning the definitions for some of the units, like for ampere, for Kelvin, for kilogram, and the mole. So these four quantities, the definitions got updated in such a way that it is decoupled from like particular experimental realizations of the quantity. So as technology improves, you'll get more precise values for these things, but the definition itself is now decoupled. And quantum metrology, which is using quantum mechanical phenomena to make precise measurements, is expected to play a big role. And I encourage you to read this paper for more details. These are some of the applications. That there are many more, but all of these are sort of very rooted in mathematics as well. Now, looking at all of this, it might look like we just put quantum in front of everything, which is, I think, sort of true. But at least for the topics I mentioned, they are legitimate. They are good research areas to work on. So it's not just science fiction. All right. So with that sort of introduction, let me jump into introducing the basics of quantum computing. I mean, feel free to stop me and ask questions if something is unclear, if I'm going fast or slow. Please feel free to give like live feedback. Okay, so it's good to have a picture in mind for the talk, or like to just understand this area in general. So let's start with some information that you store in some qubits. So I'll introduce this notation in the next slide. But for now, just think of this symbol X as information or some logical information that you're storing in some quantum bits or qubits. Now, what you want to do is implement something like Shor's algorithm. So you want to take a huge number, store it in this qubits, and then implement Shor's algorithm to factor it. And then out comes a state, a quantum state, which represents the answer. So that is something, so whatever we called as quantum algorithms in the previous slide will go into these logical operations. But the problem is, like I said, everything is noisy. So if you do it this way, your answer is likely going to be wrong because noise would have corrupted your computation. So what you do instead is you encode your information in a larger computational space by means of encoding into quantum error correcting code. We'll see what it is later today, but it's basically saying like, take your data, add some redundancy, store it in a bigger space so that you can detect and correct errors. Don't worry about this notation. NKD just means that you have sort of k qubits, like we call bits. You have k qubits of information here, and you're storing it in n larger than k qubits of information in your lab. So this information is encoded in this state, and what you have in the lab is just this state. So this somehow holds this information. You can't see this, you can only see this. And after this, you do some physical operation, like in the lab, you do lasers or you do some operations using physical mechanisms, and you arrive at a new state. But what you would like to have is that when you decode this final state, so when you remove the code away, you would hope that you end up in the right answer, because that was the whole point of doing error correction. So you take this longer, more complicated route to get to the answer you want, because you wanted to tackle noise. So for this to happen, that for this encoding and this operations and decoding to work properly, you have to make sure that every operation you wanted to do can be translated into operations that can be done in the lab. So for any code you pick, you have to translate from this logical sort of abstract space to this actual physical space with lasers and stuff. So this translation is very important, and this is what we call like synthesizing logical operators. And of course, the other part is, so there's two things in play here. So in quantum computing, there's two things in play. One is doing these computations, and the other is correcting errors. And these have to sort of happen hand in hand. And how the dynamics works exactly, we understand some parts of it, but there's lots of questions you can ask for which we don't know the answer. So it's a very, I mean, a lot of things have been done, but there's also a lot of questions to be answered. One mathematical question to keep in the back of your mind, we'll touch upon this later, is that if all the operations that you do in your lab have to act on your code states, and you want to remain in your code states because only the code protects you from errors. So you don't want to move outside your code space. So how do you design, so for an operation that you want to do in the lab, how do you make sure that it maps code states to code states, that it doesn't take you outside your code subspace? And that is a very mathematical question, and I'll hint upon this later. Okay, so that's the big picture. And so we'll start with the basics of qubits, and then we'll in the last part of the talk, we'll talk about error correction. Okay, so just to jog our memory, you might all know this, but I just thought I'll have a slide on this in case you're new to this. But so Kronecker products is an operation you can do on two matrices. It works very similarly to the tensor product. So here, if you have a capital A matrix A and B, and the entries of A are small a ij and B is pkl, then when you take the Kronecker product, what happens is you replace every entry of A by multiplying that entry with the whole matrix B. So you have a block here, which is of size B, but you scaled every entry of B by this first entry of A. And you do this at every entry. And that's how the Kronecker product works. And of course, A Kronecker B is not the same as B Kronecker A, except for some special cases. Now, the most useful property is that when you have a product of two Kronecker products, you can just do the matrix products, the component-wise matrix products first, and then the Kronecker product. And then this also extends to any number of matrices. So A Kronecker B times A prime Kronecker B prime, you first do A prime and B prime, and then take the Kronecker product. So this is a very useful property that we almost use like yeah, I mean, we use it all the time without even knowing we're using it. It's that common. Okay, now, yes, let me introduce the qubit. A qubit, to think of, is just a two-dimensional vector space over the complex numbers. So it's a length 2 vector where the first entry is alpha and the second entry is beta. Now this notation might be new to you. So you read this as ket 0. So this line and this angled bracket together is called the ket. And this was a notation that Paul Dirac introduced. It's called the Dirac notation or the bracket notation. So you read this as alpha ket 0 plus beta ket 1. And ket 0 is just your first standard basis vector of length 2. It's just 1, 0. And this is ket 1, 0, 1. So when I do alpha times 0 plus beta times ket 1, I just get a length 2 vector where the first entry is alpha and the second entry is beta. So that's what this notation means. It's just a length 2 vector. But because of reasons we'll see later, these amplitudes, alpha and beta, are called amplitudes of the state. And the state has to be normalized. So it has to have unit length. And alpha and beta are complex numbers, so you have to do absolute value of alpha squared plus absolute value of beta squared is 1. So that's what a pure quantum state is. I put this word pure because a general quantum system is represented using a 2 by 2 matrix. A single qubit general quantum state is represented by a 2 by 2 matrix. It's called a density matrix, but I won't go into that in this talk because it'll take more time. But the basic concept is that if a quantum system is in a particular well-defined state, then the system is said to be in a pure state. But if you only have sort of probabilistic knowledge of the system, meaning like you know that with probability A it's in a particular state, with probability B it's in a different state, with probability C it's in a different state, then it's called this bag of states model. So you only have a probabilistic description of the system, and to handle that general case, you work with density matrices. But if you know you're 100% sure that the system is in a particular state, then it's called a pure state. And we'll only talk about pure states in this talk. So that's a single qubit. Now what happens when you go to multiple qubits? First thing is you look at the basis vector. So here the basis vectors was just ket 0 and ket 1. When you have multiple qubits, you just take the Kronecker product of the basis vectors. So of course, for n equals 2, you have a length 4 vector. So you need 4 basis vectors. Maybe there are some questions.
No, yeah, I'm sorry to interrupt. There is a question in the chat that says, I have a question about a Kronecker product. How can we distinguish Kronecker product from tensor product? Yeah, so the way I think about it is, so for tensor product, the dimensions sort of grow. So when you take like tensor products of two things, you get like more dimensions for the resulting tensor. But for the Kronecker product, you still you take 2 matrices and take the Kronecker product, you only get a new matrix. The new matrix is larger, but it's still a 2 by 2. It's a dimension 2 tensor. Whereas for a general tensor product, the number of tensor dimensions grow. So that's the way I think about it as a data structure. Okay. Yes. So yeah. So when you have basis, so you take your basis vectors and you take the Kronecker product, and you can check that when you take the Kronecker product of, for example, 0 tensor 1, you get this vector. And the nice thing is that it only has one entry of 1. So because by the Kronecker product definition, you replace the 1 with 1 times 0, 1. So you get 0, 1 here, and then 0 times 0, 1 is 0, 0. And this entry 1, if you see, is in the second position. But if you sort of index the 4 entries of the vector as binary indices, so this is 4, it's length 4. So I can use 2 bits to represent each sort of entry. So the first entry is like 0, 0, 0, 1, 1, 0, and 1, 1. That's just the binary expansion of 0, 1, 2, 3. And you can see that the entry of 1 exactly corresponds to 0, 1, because the second entry is 0, 1. And that's why when you take the Kronecker product of these basis vectors, you can just write a vector inside the ket
and the binary vector just signifies which entry has a 1 and everything else is 0. So this notation is super useful. And you can check it for 1 tensor 0, and I've left 0 tensor 0 and 1 tensor 1, but that's how it works. Now, of course, a general pure state is a complex linear combination of these basis vectors. So ket v, where v is a binary vector of length n, and we already saw what that means for n equals 2. And you take complex linear combinations and then also normalize the vector. So that's what a pure state is. It's basically a complex vector of length 2 to the small n, which I call capital N. And the amplitudes have to be in such a way that the vector is normalized. That's what a pure state is. And what quantum mechanics says is that these pure states evolve under unitary operations. So the operations you do in the lab, except for measurements, have to be unitary, meaning that you act by a 2 to the n by 2 to the n complex matrix whose conjugate transpose is the same as its inverse, so it's unitary. So that's what these states look like. So you have a quantum system, you initialize in a pure state, and then you evolve it using unitary operations. Okay. Now let's see some simple examples of unitaries. Namely the Pauli matrices. So on a single qubit, the Pauli matrices, there are sort of 4 Hermitian Pauli matrices. So you can check that all these 4 matrices satisfy that their conjugate transposes themselves. So they're unitary. And because the conjugate transposes themselves, it's also Hermitian. And because of this, if you square these matrices, so x squared would be the identity, z squared is the identity, and y squared is also the identity. So these are all unitary and Hermitian Pauli matrices. Because they're unitary and Hermitian, we know from linear algebra that their eigenvalues are plus or minus 1. And the eigenvectors are also simple. So for the Z matrix, you see that it's diagonal. And for diagonal matrices, I mean, it's already diagonalized. So the eigenvectors are just your standard basis vectors. So ket 0 is a plus 1 eigenvector. So Z acting on ket 0, you will get back ket 0. So this is a plus 1 eigenvector, and this is a minus 1 eigenvector of Z. So it has eigenvalue minus 1. And similarly for X, you can check that this vector, which is defined as plus, which is just the uniform superposition of 0 and 1. That's the plus 1 eigenvector for X. And the minus 1 eigenvector for X is 0, ket 0 minus ket 1. And this is what in quantum mechanics we call a superposition. Like when sort of you see press articles saying like, oh, a qubit can be both 0 and 1. What they essentially mean is that the state is in a superposition of the basis state ket 0 and the basis state ket 1. If it's only one of, if the state is itself ket 0 or ket 1, then it's sort of classical because it's just these basis vectors. But what's quantum is that you can have superpositions of these as shown here. Okay, so those are our eigenvalues and eigenvectors. And these Pauli matrices also go by these names called the bit flip. That's because when you take the X matrix here and you act on 0, so X times this vector, you pick up the second, so the first column, which is 0, 1, which is 1. So X acting on ket 0 gives ket 1, and X acting on ket 1 gives ket 0. And because this binary index is flipped, this is like your classical NOT gate. So in our classical computers, in Boolean logic, we call something the NOT gate, which just flips 0 to 1 and 1 to 0. And because this is flipping this binary index inside the ket, X is called the bit flip. And the same thing happens for Z, but in a different basis. So when Z acts on the eigenvectors of X, it interchanges them. So Z acting on plus gives minus, and Z acting on minus is giving plus. So like qualitatively, both are basically flipping operators, but they just work as flip operators in a different basis. And you can do something similar for Y, but here for convenience, I've just showed how Y acts on the standard basis. Okay, so these are called flip operators. And the key sort of relation between these Pauli matrices is that two non-identity Pauli matrices anti-commute. So of course, everything commutes with identity, But if you take x and z, then x times z is equals minus z times x. So the order in which you apply x and z matters. So this anti-commutativity is like the key structure in the poly matrices. Okay, so those are the basic poly matrices. Now so we just showed like 4 matrices, but if you're familiar with group theory, it's nice to work with groups where you basically take this identity x, z, and y as your generators, and you basically form all possible all unique combinations of these matrices, and that's what is called a group. And to make it a group, we give this additional freedom of multiplying by a fourth root of unity. So you can either have I or I squared or I cubed or I to the fourth, which is just 1, I minus 1 and minus I. And with everything together, you can show that you form this group, which is called the poly group or the Heisenberg-Weil group. So this is on single qubits. This is the same from before, but I've just written Z also on the standard basis. And yeah, for n qubits, just like we did for the basis states of pure states here, you just take Kronecker products of n poly matrices. So here I have an example for 3 qubits. So let's say you have 3 qubits and all the 3 are in some basis state, ket 0, ket 1, ket 1. And you are acting by a poly matrix on each one of them. So X acting on the first qubit, Z on the second, Y on the third. And we know from the Kronecker product property that that's how things work. So when this tensor product acts on this tensor product, you just multiply them correspondingly and then take the tensor product. So so that's poly matrices and how they work for n qubits. And the very nice property about these poly matrices, so we already saw that, so this I, X, Z, and Y were Hermitian and unitary. That property sort of goes for n qubits as well. Now the nice property is that if you define an inner product on these matrices, just the Hilbert-Schmidt inner product or the trace inner product, then according to this, by this inner product, it's not very hard to show that these poly matrices, form an orthonormal basis. So meaning they are mutually orthogonal to each other under this trace, and you can basically represent all n by n complex matrices as linear combinations of these poly matrices. So it's a very useful, it has a lot of structure. It's a very useful basis to work with. And this has applications beyond quantum. Okay, any questions about pure states or poly matrices? This is a good time to ask questions. Oh, and the other thing I just want to emphasize here is that, so you're familiar with the trace of a matrix, it's basically the sum of the diagonals. You can see that for the single qubit poly matrices, only the identity has a trace. So trace of identity is 2, but trace of X is 0, Z is 0, Y is 0. And this also generalizes to n qubits. Because when you take tensor products, the trace also works nicely. So trace of this tensor product is trace of X times trace of Z times trace of Y. So the trace splits into the components. And because each one doesn't have a trace, unless everything is the identity, the whole matrix doesn't have a trace. And this is a property you have to use to prove that these form an orthonormal basis. So that's the nice thing about these poly matrices. You can find a subset of these poly matrices, which are all the Hermitian polys. They're Hermitian, they're unitary, and except the identity, everything is traceless, and they span all n by n matrices. Okay. Yeah, now that we have seen the sort of basic unitaries being polys, let's see a little more complicated unitary called the Hadamard. You might have already got introduced to this, but Hadamard is this 2 by 2 matrix. So 1, 1, 1, minus 1. And from our definitions of X and Z, you can see that it's just sum of X and Z normalized. H is unitary, Hermitian, and squares to the identity. So just like our poly matrices. Now, you can easily check that when you act by the Hadamard on the ket 0, it goes to ket plus. And if you act again, because h squared is identity, it goes back to 0. So you can jump between these two bases. We saw that z is the computational basis, the z basis, and this was the x basis, meaning it's the eigenvector of the x operator. You can switch between the bases by using the Hadamard. And the other way to see this, see how this sort of happens, is using this idea of stabilizer. And this is the basic idea about quantum error correction. So I just wanted to introduce it here itself. So when you act on this ket 0 state by Hadamard, you can directly, for example, do the matrix vector product and see what happens. But you can do this, which it reveals new things. So you know that ket 0 is the +1 eigenvector of z. So if I introduce a z in between these two, then it does nothing because z times 0 is just 0. Now after I introduce the z, between z and 0, I can introduce h dagger h, which is just identity. So again, I'm not doing anything here. But what I'll do here is I'll club all these things together and leave the h out. So h, z, h dagger, you can do a simple computation using this definition, is x. So if you conjugate the z matrix by the h matrix, you get x. And h acting on 0 is plus, so x acting on plus is plus. So what did we do here? So, I mean, we already know that h acting on 0 is plus, but what we saw here is that this statement is equivalent to saying that conjugating z produces x, meaning you took an eigenvector of z and made it an eigenvector of x by using the Hadamard. And this idea is very sort of powerful. And this is the key idea behind this Gottesman-Null theorem, which says that a lot of quantum circuits, they're formally called Clifford circuits. Clifford circuits, I mean, Clifford operations just in one line are those unitary matrices that when they conjugate a Pauli matrix, they produce a Pauli matrix. So Hadamard is an example of Clifford. Because you conjugate a Pauli matrix, you get back to Pauli matrix. So z goes to x. And similarly, if you do h, x, h dagger, you get z. And there are more matrices like this that conjugate Paulis to Paulis. Those are called Cliffords. And just by tracking these change of operations, you can efficiently simulate a lot of quantum circuits on a classical computer. Meaning, if you just build a quantum computer to do these operations, it's not very useful because you can do it efficiently on a classical computer. So this is it's a very fundamental theorem because it says what kind of circuits you need to actually get this quantum power. And the key idea is just this kind of, what's this called as stabilizer tracking. So we say z stabilizes 0, that just means 0 is a +1 eigenvector of z. So so I'll use this word stabilize later, but that's what it means. Okay. Yes, so we have introduced pure states, how they evolve, unitary operations. We saw some basic unitaries, the Pauli matrices and the Hadamard, and we saw this stabilizer tracking. Now the key sort of very quantum thing is called measurement. So if you have a quantum system in the lab, you cannot literally see it. In order to get information from it, you need to poke it. And the way to poke it and get classical information from a quantum system is called a measurement. There's a more general notion of measurement, but I'll just stick to von Neumann measurements here for simplicity. Okay, so what does von Neumann measurement mean? So in linear algebraic terms, so think of you have a big vector space. So what you do is you split the vector space into orthogonal subspaces. So you take the whole space, you just split into a bunch of subspaces, all of which are mutually orthogonal. And so once you have subspace, each subspace has its own projector, which I'm calling P sub I. So I've split this space into T subspaces here, and each Pi is a projector onto that subspace, and they're mutually orthogonal. So Pi Pj is 0 unless I equals j. So I've basically taken the whole space and just split into chunks, which are orthogonal, and I've defined projectors. And obviously, because the subspaces span the whole space, the projectors have to sum to the identity. So this is just splitting the space into pieces. After doing this, let's say you have a quantum system in the state ket phi. So it's some long vector, a complex vector. Now, if you measure with respect to this set of projectors, with respect to your particular partition of the space, quantum mechanics tells you that this is what happens. So two things happen. One is you get a classical index out of the measurement. So the measurement tells you which projection occurred. So the measurement process is going to project the state into one of these subspaces that you constructed. And the first thing is you learn the measurement that happens. So if you read the classical result I, that means the projector Pi got applied to your state, and then you normalize suitably so that this is of unit length. And this happens, this event of reading I from the measurement happens with this probability. Now this notation might be new. So we already saw that this is a ket, it's a column vector, and Pi is a matrix. And this phi is just the conjugate transpose of this column vector. So this is called bra phi, and this is called ket phi. And this is just a row vector where each entry of phi has been taken, you take the complex conjugate. And Dirac used this notation because if you want to represent an inner product, so imagine this Pi was not there, then this is just the inner product between phi and itself, and that looks like a bracket. That's why I think Dirac called it bracket. So that's the probability with which you read I. And if you read I, this is the projection that happens. So that's what quantum does. It does two things. It gives you a classical result and it changes your state. So this is sort of very new because classically, if you if you see an object or like if you measure something, if you like take a scale and measure something, you're not actually changing that thing. Like macroscopically, we don't feel like we actually changed anything. But the actual quantum mechanics says that when you do a measurement, you actually change the system itself. It gets projected onto one of these things. Okay, so that's the measurement process. And two states are different only if there exists some measurement that can distinguish them. Because the only way of distinguishing two quantum systems is using a measurement. And if there is no measurement that can differentiate between them, for all practical purposes, they are the same thing. And you can check that by this sort of mathematical definition I gave, you can take the state phi and then multiply by a complex scalar, e to the I alpha. Now, because this has norm 1, the whole thing has norm 1. This has absolute value 1. But there is no quantum measurement that can differentiate between phi and e to the I alpha phi. And so you can also think of a pure state as a ray. So it's not just the state, but the state multiplied by any complex number with absolute value 1. So was that? I hope I got the idea of measurements clear. We'll do an example now so that it becomes more clear. Okay. So we already saw the single qubit Pauli matrices. Now let's say we do a measurement that is with respect to this matrix Z. So quantum people just say, I want to measure Z. So what does that mean? That means that the projectors that define the measurement are given by the eigenvectors of this matrix Z. So when I say measure an operator, that operator has to be Hermitian, and it's called an observable. So quantum people call Z an observable. So an observable is a Hermitian matrix. And if I say I want to measure this observable, that means the projectors are given by the rank 1 projectors formed by the eigenvectors of the Hermitian matrix. So for Z, we saw that the eigenvectors are ket 0 and ket 1, and this is just the outer product. So this is the one-dimensional projector or rank 1 projector that projects onto the state 0. And similarly, this is for 1. Okay, so now that we have these projectors, we can now measure. So let's say my system was in one of these basic states. As a simple case to start with, let's say Z was 0. So my system itself is in ket 0. And then I do this measurement of Z. You can compute the two probabilities. So one probability is inner product 0, P0, 0. And because P0 is just the outer product, you get two inner products between 0 and 0. So like you get a bra 0 and then one ket here, that's one inner product. and then you have another bra 0, and then again a ket 0. That's another inner product. But both of them are 1 because 0 is norm 1. And so you always deterministically get the result 0. So there is no randomness in this measurement. If your system is in state 0, and if you're measuring with respect to these projectors, there is no way you can read a 1 because it's orthogonal to the state you have. So this is a sort of deterministic measurement. So it's sort of uninteresting. Let's see a more interesting measurement. Let's say I have the state plus or minus. So let's say just take the ket plus, for example, which is ket 0 plus ket 1 over square root of 2. Now, if you compute this probability, so the inner product between ket plus and P0, which is this, and then bra plus, and then ket plus, then you will see that the probability is half. What that means is that if you measure this superposition with respect to this projection, with respect to these projectors, then you can get a measurement 0 with probability half or a measurement 1 with probability half. And by quantum mechanics, so you get a new state, which is projected. And if you measure 0, the new state is just ket 0. If you measure 1, the new state is ket 1. All I've done is applied what I gave here in the previous slide for this particular case. So that's what happens. And this is why, for a more general state, if I just have a general state psi, we saw when I introduced qubits, we saw that it's alpha 0 plus beta 1. And what would happen is you can do this calculation and you'll see that you will measure 0 with probability more absolute value of alpha squared. And you'll measure 1 with absolute value of beta squared. And one of the two has to happen. That's why we said absolute value of alpha squared plus absolute value of beta squared should be 1. So let me quickly point that out. Yes. So here, if you take this general sort of single qubit state, you measure Z, you will get 0 with probability mod alpha squared, you'll get 1 with probability mod beta squared, and those two have to sum to 1 because they represent probabilities. The thing to remember in quantum is that the amplitudes of a state don't have a physical interpretation. They are just like complex numbers. But the absolute value squared is giving you the probability of reading that measurement when you measure in the Z basis. Okay. So that's measurement. Yeah, this is just another example. So when you can also write the standard basis 0 in terms of plus and minus. So all I'm saying here is you can go through these mechanics, but the key point of this slide is that the outcome of a measurement depends on like two things. One is how you split your space, and two, what state the system is in. Both dictate what are the possible outcomes. That's basically the point. Okay. And the other sort of quantum phenomena is called entanglement. Entanglement means that, let's say you have 2 qubits with you, and the 2 qubit state the system is in is given by this. So this is just 2 basis vectors. You have a superposition. And if you write this as a column vector, you'll get like 1, 0, 0, 1, and then 1 over square root 2 outside. And you can check that there's no way you can write this as a Kronecker product of 2 single qubit states. So this is a 2 qubit state, but you can check for yourself that this cannot be written as, like some ket psi Kronecker ket phi for any 2 single qubit states, which means the state is entangled. And entanglement, so intuitively entanglement is some sort of correlation, but these are called Bell states because John Bell used these states to demonstrate that these have correlations stronger than it is possible with classical physics. These 2 qubits have a correlation that is much stronger than you can produce just using classical mechanics. And that's called entanglement. Now, again, you can go through the mechanics of the measurement postulate, and you can check for yourself that if you measure Z on only 1 qubit, so let's say the first qubit, then the state will either collapse to ket 0, 0 or ket 1, 1. There's only 2 possibilities. So if you read 0, the new state will be just this. And if you read 1, the new state will be that. And they happen with probability half. And you can see that after measurement, because you only get one of these two states out, the second qubit is sort of deterministic. Like you don't even have to measure the second qubit. Just measuring the first qubit put the second qubit in a deterministic state. And that happened because they're entangled. So entanglement is a purely quantum phenomenon. So I've shown you sort of different sources of, in my talk, I advertised like what's fundamentally different between classical computing and quantum computing. So there are a few things that you have already seen. They all sort of interplay together to produce these extra sort of capabilities in quantum, namely superposition, meaning like you can be in a superposition of two basis states. So superposition is one thing. Entanglement is the other. So like a state can be entangled, which is not possible to produce classically. And then the third thing, I guess, is measurement. So measurement is sort of a very quantum phenomenon. And in fact, for quantum error correction to work, measurement is sort of the driving phenomenon. Okay. Again, so just like we did for single qubits, we saw that ket0 was the eigenvector for Z, and ket1 was the -1 eigenvector for Z. So we introduced this notion of stabilizer, meaning +1 eigenstates. And you can check for yourself that these two states, the stabilizers are given by these pairs of operators. So let's just do one example, just to understand what's going on. So if I take x Kronecker x and act on, phi plus, so this ket00 plus ket11, we saw that x is the bit flip. So if I act on by x Kronecker x on this state, so I have two x's on the two qubits, so both will get flipped. So this will go to 1, 1, and this will go to 0, 0. But I only had a plus here, so I'm producing the same state again. And so 0, 0 plus 1, 1. So phi plus is a +1 eigenvector of x Kronecker x. And then if you have put a minus sign, you get phi minus is the +1 eigenvector of minus x Kronecker x. And so these are, and then you can also check for Z by the definitions we had before. And so you can think, all I'm saying here is there's two ways to think about these states. You can just think about these states as these long vectors, or you can think of them as the common +1 eigenvector of these two matrices. And from the linear algebra, we know that commuting matrices can be simultaneously diagonalized, and that's the property I'm using here. These two matrices commute because we saw xz is minus zx, but that happens twice because this x anti-commutes with the z, this x also anti-commutes with the z, and the two minuses become plus. And so these two operators commute with each other. And because they commute, you can simultaneously diagonalize them, and the common +1 eigenvector is phi plus. So it's usually in a lot of cases, it's very convenient to think of just these stabilizers, like the matrices that fix the state, rather than the state itself, because the state grows exponentially. And these Pauli matrices are easier to keep track of. Okay, so that covers, all the basics I want to talk about. I think I had more stuff in quantum error correction than I might have. So how much time do I have, Shanshan? 5?
Yeah, 5 minutes. Yeah.
Okay. So I'll maybe just, I'm happy to share the slides as well. I can email Shanshan and she can forward it to everyone. So I might not have enough time to talk about everything I had in quantum error correction, but I'll just touch on the key points, and hopefully with the background I gave, you'll be able to connect the points. Okay. So with that basics, let's get some intuition for what error correction means. So let's just think of bits for a second. So let's say you have one bit that you wanted to communicate to someone, right? So, but the channel you're using, like your cell phone or whatever, the actual channel through which the bit is passing is noisy. So it's likely to sort of flip your bit. So if you just send a 0, that's your information. And if, for example, you send it to Shanshan and Shanshan receives 1, there's no way for her to know that you intended to send 0 because she just saw 1 and she'll just think that you sent a 1. So if you only transmit raw information, there is no way to detect errors. And the thing that humans do all the time is just repeat. Like if you talk on the phone to someone, if you can't hear them, you just say like, can you repeat once again? Can you repeat once again? Until you're like confident about what they said, you just ask them to repeat. So that's a good strategy. But we also don't want to waste too many resources. So like here I could just repeat the bit 3 times. And at the receiver, I can just take a majority word. So if I send the same bit 3 times and the channel flipped one of the transmissions, then again, 2 of them are correct. And so if I just do the majority word, I'll get the answer right. But of course, if the channel flips 2 of the 3 bits, then I will decode to the wrong information, because if I receive 0, 1, 1, I'll think that 1, 1, 1 was transmitted and 1 was a single flip occurred, because that's more probable to happen. Like 2 bits getting flipped is rarer. That's the key idea. So you just add redundancy to the data. And there's a more formal way of saying this. Because it's easy to check, I'll gloss over the details. But formally, linear codes classically are just defined as the null space of a matrix H. And this null space is taken over the binary space, so not over real numbers. So think of this H as a binary matrix. And you can check that these 2 vectors are in the null space of this matrix. So meaning H times 0, 0, 0 will be 0. H times 1, 1, 1 will be 1, 0. So the code is just a subspace that is defined as the null space of this matrix. And then there's a systematic way to detect what error happened. And depending on what error model you use, like if you have a crazy error model where like two bits getting flipped is more likely than 1 bit getting flipped, I mean, that's unusual. But if you had that kind of an error model, then you should decode based on your error model. So the error model I just said is the natural one, where each bit is, say, flipped independently. And then if you work out the math, you can see that if you receive a 0, 0, 1, then the most likely thing is 0, 0, 0 was what got transmitted. So there's a systematic theory here. And what classical coding theory people study is just repeating bits sort of consumes more resources, although it's super reliable. So there's a sort of rate reliability trade-off. So here I'm using like 3 bits to communicate 1 bit of information. So my rate is 1/3, but I'm also getting some reliability out of it. And then there is other trade-offs. So what classical coding people study is what kind of coding schemes I should use so that I don't use too many physical resources to protect from the errors that happen. That's what coding is all about. Now in quantum, unfortunately, there's this no cloning theorem, which says that you cannot copy bits. So if you have a quantum state, if you have a qubit of information and you don't know what it is, then it's impossible to copy it. Like unless the qubit itself was a classical sort of state, meaning like one of these basis states, then it's impossible to clone. So no cloning theorem sort of shows up everywhere because you can't copy information. But there exists something like a repetition code. The only thing is that the basis states get repeated. But if you had a superposition of the basis state, then the encoded version of it is not just a repetition. So like if I had the plus state, and if I encode into this code, it's not just 3 copies of the plus state, but something more complicated. And this is an entangled state. And so we are basically storing information in entanglement. And the idea here of quantum error correction, I just get the key idea out, is that for the code that you define a stabilizer group, which is a set of commuting Pauli matrices, just like we did for these entangled states. And you can check that if you act by Z Kronecker I on the state, you get the state back. So meaning this is a +1 eigenvector of this and a +1 eigenvector of this. So for any alpha beta. And alpha beta is your degree of freedom to store information. So all the information you have on this 1 qubit is stored in this alpha and beta. And the way you check for errors is you check if this operator fixes the state. If it doesn't fix, then you know that something is wrong, and then you correct accordingly. So the idea of quantum error correction is to store information in entangled states, and then define this stabilizer group, which gives you sort of parity checks, which says that the state should always be a +1 eigenvector of these matrices. If at some point you realize it is not, then something is wrong. And then there's a way to figure out what was wrong and so on. But I think I'm almost at time. This is just the formalism. I think from the classical error correction slide, this should be hopefully clear. The last thing I wanted to say is, getting back to this picture that I showed first. So we saw, the basic idea of quantum error correction, although couldn't get into much detail. But the thing is not only about protecting errors, right? Because for the example I showed you, we had 1 qubit of information and we stored it in 3 qubits in the lab. But if you want to do an operation on the 1 qubit, then you have to figure out what operation on the 3 qubits you can do in the labs such that the 1 qubit operation gets induced. And that's the area in which I worked primarily during my PhD. And this is also an example. That produces a lot of beautiful math problems. So we already saw the Hadamard, but there are more things. Remember in the Gottesman-Nil theorem, I said something about these Clifford operations. So the first 3 rows actually are sort of generators. So any Clifford operation can be written as a combination of these operations. But we know from the theorem that these can be simulated efficiently on a classical computer. And so you need this extra thing. This extra thing can be anything that's not Clifford, but the standard example is what's called the T-gate. And we introduced a formalism in my PhD to sort of systematically connect it with the existing knowledge of Cliffords. So that's called Q of T-gates. And the other thing we did is we showed how to systematically sort of synthesize these logical operations for these different. So for like Cliffords, we did first paper, and then the second paper became sort of more interesting because it's usually harder to do. And this is the paper where we were able to address a sort of a long-standing open question. Okay, so just to recap, we saw that pure states are normalized normalized vectors. Then we saw that the Pauli matrices form orthonormal basis. We saw what measurement does. It gives you an output, which is the eigenvalue, and then it projects onto an eigenvector. Commuting Pauli matrices are called stabilizers, and we define quantum codes as the common +1 eigenspace of all the elements of the stabilizer. And if you have if you have n qubits, and if you have n independent Pauli matrices fixing the state, then it's a unique state, meaning the subspace is just one state. But if you have n qubits and if you have n-1 generators, then you have 1 qubit of space to store information. It's not a unique state, it's a subspace. So how many generators you have for the stabilizer determine the degree of freedom you have to store information. And yeah, you use stabilizer measurements to plot the state and see if something went wrong. And if something went wrong, there's a way to find what went wrong and then fix it. So code can be different in different ways, but I couldn't get into this too much. And the final thing is you have to sort of balance this decoding with also doing logical operations. And these logical operations should also be protected from noise. That's called fault-tolerant quantum computing. Hopefully I was able to convey at least a big picture idea of what the field is about. And for more information, I encourage you to look at my dissertation. I wrote it in such a way that there's sort of enough background for anyone to pick up. So it's like, to a good extent, it's self-contained. And in particular, chapters 2 and 4 of my thesis has a lot of background about quantum computing and quantum mechanics. Thank you so much.
Well, thank you so much, Narayan. And are there any questions from the audience?
I have a quick basic question. Can you explain why there's a need to use complex numbers to represent states, and how do they measure them in the lab?
Yeah, so, right. So, I mean, I guess it's sort of an artifact of physics. I don't know how best to put it, but I think the way that quantum mechanics works is that, it's a postulate that basically says that quantum systems can be represented as these long vectors with complex entries. And I guess physicists just needed this degree of freedom given by these complex numbers, which we call the amplitudes. And only using that theory, they are able to make predictions which coincide with experiments in the lab. So I guess it's just, I mean, at some point, it's just a theory that works, but you would have to ask a proper physicist to give a more deeper explanation. Fortunately, I don't think I'm capable of doing that.
So do they actually measure them in laser? Like, how do you get complex numbers in the lab?
Yeah, so you don't actually, so what happens is there's always sort of a global phase degree of freedom. Like we saw that a state psi, you can multiply by some e to the I theta and nothing changes. There's always that phase degree of freedom. But what you can do is if you prepare this state like 1,000,000 times in the lab, and each time you prepare and measure in the z basis, right? Then the result is going to be 0 or 1. And then you count that. So you count how many times you get 0 and how many times you get 1. And that gives you an estimate for mod alpha squared and mod beta squared. And then there's ways to sort of measure the relative phases. So using this sort of repeated measurements, you can estimate these amplitude squares. But if you need the amplitude itself, you cannot just take the square root of this because there's an extra phase. Of course, global phases don't matter, but relative phases matter. Like the relative phase between alpha and beta matters, and there's ways to measure that aspect.
Other questions? You can simply unmute yourself or type your question in the chat.
Can I ask a question? Like, I was wondering, because you mentioned like a lot of measurements in the lab. I was wondering, besides the measurements, like what other kinds of research is really happening in a lab?
Yeah. So So when, for example, a few things. So we saw these Pauli matrices. So on paper, there's these like square matrices that get applied on the state. But in the lab, for example, I'm a little more familiar with ion traps because at Duke we had ion traps. So in ion traps, what you have to do is everything. So all these sort of lab operations you can do is like rotations about some axis. So these Pauli X and Z matrices, you can actually represent them as a coordinate system. And Z, so if you're doing, if you're applying the Z matrix, that means you're rotating this state, this pure state, which is a complex vector and lying in some complex plane. You're rotating it by some angle. And so in the lab, they have to worry about like, how do you implement lasers such that the state exactly gets rotated by that angle? Because if it gets a little over rotated or under rotated, that sort of has a residual error, which if it happens only once, it's fine. But if it keeps happening over and over, then the error can build up. And those are called coherent errors. So people worry about that. And people worry about, like how to reliably do measurements. A lot of times your measurement apparatus, for example, in ion traps, the way they measure is you have a qubit that's say in the ground state or in the excited state. So the 0 state or the 1 state, think of that as the ground state or the excited state. The way they detect if it's in the excited state is when they do the measurement, it sort of gives out light. And they have schemes to detect this, detect the photons that the state emitted when it went from the excited state to the ground state. And detecting those photons, if you detected some sort of threshold of photons, then you decode it as a 1. Otherwise, you estimate it as a 0. Now that's, like the high level description of what a measurement does. But this measurement apparatus itself can be very unreliable. Sometimes it like misses photons, or if sometimes has like dark counts, meaning like even if there's no photon, sometimes it picks up photons. So they have to worry about doing all these things reliably. So that's, yeah. So, I mean, every sort of operation you have to do on the state, you have to figure out a way of doing it reliably in the technology you're using. So I guess that's the broad state. I mean, and that covers so many things, which I'm not completely aware of.
Thank you.
Did that answer your question?
Yes. It answers my question.
All right, I think we are running out of time, and let's thank Narayana again for this really great talk. I feel like I learned a lot about quantum computing. I am no expert in this field, so thank you so much. And as Narayana said, I will send the slides as well as his contact information. So if you have questions, feel free to email Narayana. But thank you everyone for coming to the MathStat Tea. I think next session will also be on Thursday. But please check the announcement in the email. Have a good rest of your day, everyone. Thank you for coming.
Thank you so much. Thank you so much for having me here.